Let's explore C++ multisets. Multisets are ordered containers in C++ that allow duplicate elements. They are provided by the standard template library, also known as STL, through the std multiset class. Let's see what are the features of it. Multisets are part of the C++ standard template library, or STL. They are defined in the set header file. Multisets maintain elements in a sorted order. The key difference between a multiset and a set is that multisets allow duplicate elements, unlike standard sets. Multisets are typically implemented as balanced binary search trees, ensuring that most operations have logarithmic time complexity. Now, let's look at a basic multiset declaration and initialization example. First, include the necessary headers, set and iostream. Then, in the main function, create a multiset of integers named numbers. You can insert elements into the multiset using the insert function. Notice that we are inserting the value 10 twice, which is allowed in a multiset. This demonstrates the basic declaration and initialization of a multiset with duplicate values. There are several ways to create and initialize multisets in C++. Let's start with the default constructor, which creates an empty multiset. Next, you can initialize a multiset with specific values directly during declaration. Here ms2 is initialized with several integer values, including duplicates. The multiset will automatically sort these values. A multiset can also be created as a copy of another multiset, using the copy constructor. Here ms3 is a copy of ms2. Finally, you can create a multiset from a range of elements such as those in a vector. Here ms4 is initialized with the elements from the vector, vec, using the range constructor. Let's discuss some basic operations you can perform on multisets. Here's a table summarizing the common methods: insert, erase, find, count, size, and empty. The insert method adds elements to the multiset. The erase method removes elements from the multiset. The find method searches for an element and returns an iterator. The count method returns the number of occurrences of a specific element. The size method returns the total number of elements in the multiset, and the empty method checks if the multiset is empty. Here's a code example illustrating these operations. First, we include the necessary headers, set and iostream. Next, we create a multiset named ms, initializing it with some values, including duplicates. We then insert the element 3 into the multiset. To count the occurrences of the element 2, we use the count method, which returns 2 in this case. To find the element 4, we use the find method, which returns an iterator pointing to the element. Finally, to erase all occurrences of the element 2, we use the erase method. Multisets maintain their elements in sorted order, making it easy to iterate through them. Let's explore 2 common ways to iterate through a multiset. Here is a code example. First, we include the set and iostream headers. We then create a multiset named ms and initialize it with some values. The first method is using a range-base for loop, which provides a clean and simple way to iterate through each element in the multiset. Each element is accessed directly in the loop. The second method uses iterators. You initialize an iterator to the beginning of the multiset, and then loop through the multiset until you reach the end. Inside the loop, you can access the current element using the dereference operator. Let's explore some advanced operations available for multisets, specifically range operations. Here's a table summarizing these methods: lower underscore bound, upper underscore bound, equal underscore range, in place, and in place underscore hint. The lower underscore bound method returns an iterator to the first element that is greater than or equal to a given value. The upper underscore bound method returns an iterator to the first element that is greater than a given value. The equal underscore range method returns a pair of iterators that specify a range containing all elements equal to a given value. The inplace method constructs a new element in place, avoiding unnecessary copying or moving. The emplace_hint method is similar to emplace but takes an iterator as a hint to where the element should be inserted, potentially improving performance. Here's a code example illustrating these operations. We include the set and IOStream headers. Then we create a multiset named MS, initializing it with some values, including duplicates. To find the range of all elements equal to 2, we use the equal_range method, which returns a pair of iterators. We then loop through this range and print the elements. To find the first element that is greater than or equal to 3, we use the lower_bound method, which returns an iterator pointing to that element. Multisets use a default comparison function to sort elements, but you can customize this behavior by providing your own comparator. Let's see the key aspects of using custom sorting. You define your own ordering logic. You pass the comparator as a template parameter when declaring the multiset. You can use function objects, also known as functors, or lambda expressions as comparators. Custom comparators are particularly useful when working with custom data types. In this example, we define a custom comparator named descending order, which sorts integers in descending order. In the main function, we create a multiset of integers using the descending order comparator. When elements are inserted into this multiset, they will be sorted according to the custom comparator. Let's explore some practical applications of multisets. Here are 3 use cases. Frequency counting, where you can track the number of occurrences of elements while maintaining sorted order. Text processing, where you can store and analyze word frequencies in documents. Event scheduling, where you can manage multiple events occurring at the same time. In summary, multisets are ordered containers that allow duplicate elements. They offer logarithmic time complexity for most operations. They are particularly useful when both order and duplicates are important. Additionally, they provide powerful range operations for efficiently working with sorted data. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.